On December 14, 2009, NASA's Fermi Space Telescope was flying over Egypt when it detected a strange burst of particles. The storm responsible was nowhere nearby. It was over Zambia, approximately 4,500 kilometers away and below the satellite's horizon. Fermi could not see the storm. Instead, the storm had launched a particle beam into space. The particles followed Earth's magnetic field and struck the spacecraft. Part of the beam then reflected from a magnetic mirror point and hit Fermi again just 23 milliseconds later. Inside that beam was antimatter. Antimatter sounds like something that should exist only inside an advanced laboratory or a science fiction weapon. But thunderstorms can produce it naturally in Earth's atmosphere. To understand how, we first need one particle, the positron. A positron has the same mass as an electron, but the opposite electrical charge. It is the electron's antimatter counterpart. When a positron meets an ordinary electron, they annihilate. Their mass is converted into energy, usually producing gamma rays with a very specific signature, 511,000 electron volts. That exact signature is what Fermi detected. For most of history, lightning was understood mainly as an enormous electrical discharge. But in 1994, a satellite built to observe gamma-ray bursts from deep space detected intense flashes coming from Earth's atmosphere. Scientists named them terrestrial gamma-ray flashes, or TGFs. They are extremely brief, often lasting less than a millisecond, yet they contain some of the highest energy radiation produced naturally on Earth. A thunderstorm, it turns out, can behave like a giant particle accelerator. Inside a storm cloud, powerful electric fields can accelerate free electrons to nearly the speed of light. As these electrons collide with air molecules and are deflected, they release high-energy gamma rays. Some of those gamma rays carry enough energy to create a particle pair, one electron and one positron. The particles can then travel along Earth's magnetic field, forming beams that may reach satellites hundreds of kilometers above the planet. But scientists later discovered an even stranger process happening closer to the ground. On February 6, 2017, a winter thunderstorm passed over the coast of Japan. A network of radiation detectors was positioned between half a kilometer and 1.7 kilometers from a lightning discharge. First, the instruments recorded an intense gamma-ray flash lasting less than 1,000th of a second. Then came a brief afterglow that faded within a fraction of a second. Finally, the detectors recorded gamma rays at the unmistakable energy produced when positrons annihilate with electrons. This signal continued for approximately 1 minute. The sequence revealed an entire chain of nuclear reactions taking place inside ordinary air. The first gamma rays were energetic enough to strike the nuclei of nitrogen atoms. In some collisions, a gamma ray knocked a neutron out of nitrogen-14. That transformed the stable nitrogen into nitrogen-13, a radioactive isotope. The released neutrons collided with other atoms, producing the brief gamma-ray afterglow. Meanwhile, the newly created nitrogen-13 began to decay. During that decay, it emitted positrons. Those positrons soon encountered electrons in the surrounding air. Matter met antimatter. Both particles disappeared, and their energy emerged as gamma rays. The detectors did not observe the positrons directly. They detected the precise 511 kilo electron volt signature left behind when the positrons were annihilated. This provided conclusive evidence that natural lightning had triggered nuclear reactions and produced neutrons, radioactive isotopes, and antimatter in Earth's atmosphere. That does not mean every lightning bolt is a miniature nuclear bomb. There is no runaway chain reaction, and the amount of antimatter involved is tiny. Positrons survive only briefly, because ordinary matter surrounds them everywhere. Most disappear almost immediately after encountering electrons. The familiar dangers of a thunderstorm, including electrocution, fire, falling trees, and violent winds, remain far more important to someone on the ground. What makes the discovery remarkable is not its destructive power. It is the environment in which it happens. We normally associate nuclear reactions with stars, reactors, and specialized laboratories. Yet the atmosphere can perform them using ordinary gases and the immense electric fields inside a storm. And the discovery was almost accidental. The first terrestrial gamma-ray flashes were found by a spacecraft looking for explosions in the distant universe. Fermi was designed to study cosmic radiation, yet it detected antimatter, launched by weather beneath it. Ground instruments in Japan later showed that the atmosphere itself can briefly become a factory for radioactive isotopes and positrons. Scientists are still investigating exactly how thunderstorm electric fields initiate these extreme events, why only certain lightning events produce detectable gamma-ray flashes, and how frequently the strongest reactions occur. But the central fact is established. When lightning flashes, the event may involve far more than visible light, heat, and thunder. For a fraction of a second, electrons can accelerate to almost the speed of light. Gamma rays can knock neutrons out of atomic nuclei. New radioactive atoms can appear, and particles of antimatter can be born in the sky. A thundercloud may look like nothing more than water, wind, and darkness. But hidden inside it is one of nature's most unexpected laboratories, a particle accelerator suspended above our heads.